Have you ever looked up at the night sky and felt that eerie sense of wonder, like the universe is hiding secrets just beyond our grasp? Picture this: somewhere out there, a star vanishes without a trace. A black hole defies the very laws of physics. A cosmic void stretches hundreds of millions of light years, empty in a way that shouldn't be possible. These aren't plot twists from a sci-fi novel. They're real phenomena lurking in the depths of space, waiting to shatter everything we think we know. The universe is supposed to follow rules: gravity, thermodynamics, the speed of light. But what happens when it doesn't? When the cosmos throws us a curveball so bizarre, even the brightest minds can only stare in stunned silence. That's where the real magic happens. Today, we're diving into 20 of the most jaw-dropping mysteries that science still can't explain. Glowing stars that flicker like faulty streetlights. Unexplained radio signals from the void. Entire galaxies moving towards something we can't see. Each one is a cosmic riddle, whispering that our understanding of reality might be hanging by a thread. This isn't just about stargazing or ticking off a list of oddities. It's about standing at the edge of human knowledge and peering into the unknown. Whether you're an armchair astronomer or someone who just loves a good mystery, these enigmas will pull you in, not just with their strangeness, but with the thrilling possibility that solving them could rewrite science itself. So take a deep breath. The universe is about to get a whole lot weirder. Imagine a hole in the universe so vast it could swallow thousands of galaxies without leaving a trace. The Boötes Void isn't just empty, it's a staggering cosmic anomaly, a bubble of near-nothingness stretching 330 million light-years across. To put that into perspective, if you drop the Milky Way into this void, its nearest neighbor would be tens of millions of light-years away. Most regions of space are teeming with galaxies, clustered together like cities in the night. But the Boötes Void, it's more like a deserted highway stretching into oblivion. Scientists first stumbled upon this eerie emptiness in the 1980s while mapping the cosmos. They expected to find galaxies scattered evenly, like sprinkles on a cupcake. Instead, they found a gaping hole in the celestial fabric. The void contains only a handful of galaxies, about 60 compared to the thousands that should be there. It's so unusually barren that astronomers nicknamed it the Great Nothing. And here's the kicker: according to our current understanding of the Big Bang and cosmic structure, something this empty shouldn't exist. The universe is supposed to be speckled with matter, not pockmarked by voids this extreme. So what could have carved out such a colossal absence? One theory points to an unfathomable cosmic event, perhaps the collision of multiple smaller voids merging into one gigantic emptiness. Others speculate about quantum fluctuations in the early universe, tiny ripples in space-time that somehow ballooned into this vast desert. Then there's the more speculative idea: could an ancient, hyper-advanced civilization have harnessed the energy of entire galaxies, leaving behind this sterile expanse? It sounds like science fiction, but the sheer scale of the void forces us to consider even the wildest possibilities. Whatever the cause, the Boötes Void challenges everything we think we know about how the universe organizes itself. It's like finding a blank page in the middle of an epic novel, a glaring omission that hints at missing chapters in our cosmic story. And here's the real twist: this void isn't alone. Astronomers have found other similar voids, though none as dramatically empty. Could these gaps be flaws in our models, or are they clues to something deeper, something we haven't even begun to grasp? For now, the Boötes Void remains one of space's most haunting mysteries. It's a reminder that the universe doesn't always follow the rules. and that sometimes the most profound questions come not from what's out there, but from what isn't. What if the universe had a delete button, one so powerful it could erase the very fabric of reality? That's essentially the puzzle at the heart of the black hole information paradox. At first glance, it sounds like something ripped from a physicist's nightmare. According to the unshakable laws of quantum mechanics, information can never truly vanish. Every particle, every ripple of energy leaves an indelible mark on the cosmos, like fingerprints on glass. But black holes, they seem to laugh in the face of this rule. Swallow something into a black hole, and according to Einstein's theory of relativity, it's gone forever, crushed into oblivion at the singularity. Poof. No traces, no clues, no way to reconstruct what fell in. This isn't just some academic debate. It's a full-blown crisis at the foundation of modern physics. On one side, you've got quantum mechanics, which insists that information is sacred. It might get scrambled, but it can't be destroyed. Think of it like burning a book. The pages turn to ash, but in theory, if you could track every molecule of smoke and ember, you could reverse the process and reconstruct the original text. Now imagine tossing that book into a black hole. Quantum mechanics says the information must still exist somewhere, but relativity says it's been wiped from the universe entirely. That contradiction isn't just a gap in our knowledge, it's a chasm, revealing that our two most successful theories of reality might be fundamentally incompatible. Enter Stephen Hawking. In the 1970s, he proposed a groundbreaking idea. Black holes aren't completely black. They slowly leak energy, now known as Hawking radiation, and over eons, they evaporate entirely. At first, this seemed to solve the paradox. The information might escape, encoded in that radiation. But here's the catch: Hawking radiation is random, like static noise. It carries no obvious trace of what fell in. So even if the information isn't destroyed, it's been scrambled beyond recognition, like a blender turning a library into alphabet soup. That left physicists with two equally unsettling options. Either information really is lost, which breaks quantum theory, or there's some hidden mechanism we don't yet understand. The stakes couldn't be higher. If black holes truly erase information, it would mean rewriting quantum mechanics, a theory that's been tested with pinpoint accuracy for over a century. On the other hand, if the information survives, it implies there's a layer of reality deeper than spacetime itself, perhaps holographic, where data is stored on the black hole's event horizon like a cosmic hard drive. Some theories even suggest that black holes might be portals to other universes, with the information reborn elsewhere. Wild as it sounds, each possibility forces us to rethink the nature of existence. What makes this paradox so thrilling isn't just the mystery, it's the potential for revolution. Every time science hits a wall like this, it's a signpost pointing to something bigger. The black hole information paradox isn't just a puzzle to solve. It's a doorway, one that might lead us to the long-sought theory of quantum gravity, or even reveal that spacetime is an illusion. For now, the debate rages on, with labs around the world testing ideas from string theory to loop quantum gravity. But one thing's certain: whatever the answer turns out to be, it won't just explain black holes, it'll redefine reality itself. There's a silent river flowing through the cosmos, one that shouldn't exist. Imagine tossing a handful of leaves into a calm pond, only to watch them all drift in the same direction, defying the wind and currents. That's the essence of dark flow, a baffling phenomenon where entire clusters of galaxies are being pulled towards something unseen, something beyond the edge of our observable universe. These aren't just random motions, they're coordinated, like invisible hands tugging at the fabric of spacetime itself. And here's what makes it so unsettling. According to the Big Bang Theory, the universe should be expanding uniformly, with galaxies scattering outward like shrapnel from an explosion. But dark flow throws a wrench into that tidy picture, suggesting there's a colossal something out there, something so massive it's bending the rules of cosmic behavior. Scientists first noticed this anomaly in 2008, while studying the motion of galaxy clusters using X-ray telescopes. They expected to see the gentle drift of expansion, but instead they found clusters hurtling at speeds exceeding 1,000 kilometers per second, all toward the same patch of nothingness. The sheer scale of this movement is staggering. We're not talking about a few rogue galaxies. It's as if the entire local universe is caught in a current, flowing toward an uncharted destination. The most obvious explanation, gravity, but here's the catch. There's nothing in our observable universe massive enough to exert such a pull. That leaves two spine-tingling possibilities. Either there's an unimaginably vast structure lurking just beyond our cosmic horizon, a supercluster of galaxies so enormous it dwarfs everything we've ever seen, or our universe is feeling the gravitational tug of another universe entirely. The idea of a parallel universe might sound like science fiction, but it's rooted in legitimate theoretical physics. Some models of the multiverse suggest that our universe is just one bubble in an infinite froth of others, each with its own physical laws. If one of those bubbles happened to brush against ours, its gravity could theoretically reach across the void, creating this mysterious flow. Of course, not everyone's convinced. Skeptics argue that dark flow might be a statistical fluke or an artifact of measurement errors, yet the evidence keeps piling up. Recent studies have confirmed the phenomenon across even larger distances, deepening the mystery. What makes dark flow so electrifying isn't just the what, but the why. If it's real, it means our universe isn't the self-contained arena we thought it was. There could be realms beyond our cosmic horizon, exerting influence in ways we're only beginning to detect. It's like living in a house and suddenly realizing the walls are paper thin, with neighbors you never knew existed. For now, dark flow remains one of cosmology's most tantalizing puzzles, a whisper from the unknown, hinting that the universe's greatest secrets might lie just out of sight. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing trillions of stars. Statistically speaking, the cosmos should be teeming with intelligent life. So why does it feel like we're the only ones here? This eerie contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a question that haunts astronomers and philosophers alike. If life is common, why haven't we detected a single whisper of alien civilization? The silence isn't just puzzling, it's borderline unnerving. One possible answer is as grim as it is simple. Maybe civilizations don't last. The idea that intelligent species inevitably destroy themselves, whether through war, environmental collapse, or runaway technology, has been called the Great Filter. This theory suggests that somewhere between the rise of life and the development of interstellar communication, something wipes civilizations out, the terrifying implication. Humanity might be hurtling toward the same fate, but there's a flip side. If we find even microbial life on Mars or Europa, it could mean the Great Filter is behind us, that surviving to our stage is the rare part. That would make Earth's continued existence both a miracle and a warning. Then there's the possibility that we're just early to the party. The universe is 13.8 billion years old, but complex life might still be in its infancy. Stars and planets formed much later in cosmic history, so it's plausible that other civilizations simply haven't had time to emerge yet. We could be among the first, destined to one day become the ancient elders of the galaxy. Or perhaps intelligent life is exceedingly rare, an accident of chemistry and circumstance that makes Earth a cosmic fluke. But what if the truth is stranger? Some argue that advanced civilizations are out there, but they're deliberately avoiding us. The zoo hypothesis suggests aliens might be observing us from afar, like wildlife in a preserve, waiting for humanity to reach a certain maturity before making contact. Others propose that we're looking for signs of life. All wrong. Maybe aliens communicate in ways we can't detect, using neutrino beams or quantum entanglement. There's even the unsettling idea that we're living in a simulation, and the silence is just part of the programming. The Fermi Paradox isn't just about aliens, it's a mirror reflecting our own place in the cosmos. Every radio silence, every empty exoplanet forces us to confront how little we truly understand. Are we alone? Are we doomed? Or is the universe just playing a longer game than we can see? Until we find answers, the paradox remains a haunting reminder that the greatest mysteries aren't just out there, they're about us. One moment, the cosmos is silent. The next, a burst of radio waves brighter than 1 billion suns erupts across the universe, then vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, some of the most explosive and enigmatic signals ever detected. Unlike pulsars or quasars, which pulse with predictable rhythms, FRBs strike without warning, often never repeating. But a handful defy expectations, flashing again and again in patterns that deepen the mystery. What could possibly produce such intense, fleeting energy, and why do some echo while others disappear forever? The first FRB was discovered in 2007, buried in old radio telescope data. At the time, astronomers dismissed it as a glitch until more appeared. These bursts pack more energy than the sun emits in decades, all compressed into milliseconds. Some come from galaxies billions of light-years away, meaning whatever created them is unthinkably powerful. The leading theory points to magnetars, ultra-dense neutron stars with magnetic fields so strong they could strip atoms apart. When these stars quake or flare, they might unleash FRBs like cosmic lightning, but not all bursts fit this mold. One repeating FRB, named 1211-2 after its coordinates, pulses every 16 days like clockwork, a rhythm no known natural process easily explains. Then there's the tantalizing possibility of artificial origins. Could FRBs be alien signals, intentional transmissions meant to announce another civilization's presence? The idea isn't as far-fetched as it sounds. A sufficiently advanced society might use focused radio beams to propel spacecraft, creating bursts detectable across the universe. Or perhaps they're navigation beacons, galactic lighthouses guiding travelers through the void. Even more intriguing is the notion that some FRBs exhibit dispersion measures, clues that their signals have traveled through vast clouds of plasma, as if someone aimed them deliberately to encode information. Yet for every theory, there's a wrinkle. If FRBs were alien messages, why are they so chaotic? Why scatter them across the cosmos instead of targeting likely stars? And why would natural processes produce both one-off bursts and precise repeaters? The lack of answers has turned FRBs into a cosmic Rorschach test scientists see what they're primed to see. Some argue they're the birth cries of black holes. Others suggest colliding neutron stars or even exotic cosmic strings from the early universe. Each new detection adds complexity. In 2020, astronomers traced an FRB to a spiral galaxy surprisingly like our own, not the turbulent, star-forming regions where magnetars thrive. Another burst arrived with a side of X-rays, a first that left theorists scrambling. The more we learn, the clearer it becomes. FRBs aren't just cosmic static. They're a language we haven't decoded, written in the universe's rawest energy. Whether natural or artificial, they're proof that deep space still holds surprises capable of rewriting the rules. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that astronomer Jerry Amon circled it on the printout in red pen and scribbled a single word beside it: wow. That brief 72-second burst of radio waves would become one of the most debated mysteries in the search for extraterrestrial intelligence. Unlike the static hum of cosmic background noise, this signal was narrowly focused, blaring at the exact frequency hydrogen emits naturally, a frequency scientists had long theorized aliens might use to broadcast their presence. It was as if the universe had shouted directly at us, then immediately clammed up. The wow signal wasn't just strong, it was eerily structured. It appeared to originate near the constellation Sagittarius, rising in intensity and then fading cleanly, like a spotlight sweeping across the telescope's receiver. But when researchers scrambled to listen again, they heard nothing. No repeats, no echoes, no traces. For decades, astronomers have pointed telescopes at the same patch of sky, hoping to catch another whisper. Yet silence reigns, so what was it? The most tantalizing possibility is that we intercepted an alien transmission, a fleeting hello from a civilization that either didn't realize we were listening or didn't care to follow up. But skeptics have other ideas. Could it have been a rogue satellite passing overhead, reflecting a human-made signal back to Earth? Unlikely. No known satellites match the signal's profile. A natural cosmic event, like a comet emitting hydrogen. The timing doesn't line up. No comets were in the area at the time. Some argue it might have been a previously unknown astrophysical phenomenon, a one-off burst of energy from a dying star or colliding asteroids. Yet nothing in the decades since has behaved quite like the wow signal. Its uniqueness is what makes it so haunting. What elevates this mystery beyond mere curiosity is the signal's precision. It wasn't random noise, it was tuned to a frequency that cuts through the cosmic static, exactly where scientists had predicted an intelligent message might appear. That specificity is hard to dismiss as coincidence. If it wasn't aliens, it was something equally extraordinary. A natural event we've never seen before, or a technological glitch so bizarre it's never been replicated. The wow signal lingers in the collective imagination because it's the ultimate cosmic tease. For 72 seconds, the universe seemed to wink at us, offering a clue, or maybe just a riddle. Whether it was a distant civilization's discarded beacon or a freakish cosmic hiccup, one thing's certain. In the vast, noisy expanse of space, no signal has ever made us feel so deliberately noticed. Or so utterly alone. Most stars flicker gently, like candles in a breeze, but Tabby's star doesn't just flicker. It plunges into darkness without warning, dimming by as much as 22% before brightening again, as if something colossal is passing in front of it. Located 1,400 light-years away in the constellation Cygnus, this star, officially named KIC 8462852, has baffled astronomers since its bizarre behavior was first spotted in 2015. The dips in brightness aren't regular like those caused by orbiting planets. They're erratic, dramatic, and utterly unpredictable. At first, scientists assumed it was just a swarm of comets or a thick dust cloud obscuring the light. But the more they studied it, the less those explanations held up. Enter the Dyson sphere, a mind-bending concept dreamed up by physicist Freeman Dyson in the 1960s. The idea was simple. An advanced civilization might build a massive structure around its star to harness every drop of energy, like a cosmic solar panel. Such a megastructure wouldn't be solid. It might consist of a swarm of orbiting collectors, blotting out portions of the star's light in irregular patterns. When astronomers realized Tabby's star's dimming matched no known natural phenomenon, the Dyson sphere hypothesis exploded into the spotlight. Could this be the first hard evidence of alien engineering on an unimaginable scale? Of course, extraordinary claims require extraordinary evidence. Skeptics point out that space is full of oddities we don't fully understand. Maybe Tabby's star is surrounded by a peculiar ring system or a vast debris field from a catastrophic planetary collision. Some suggest the star itself is unstable, with internal processes causing its light to falter in strange ways. Others propose a more mundane explanation: instrumental error or data glitches. Yet none of these theories fully account for the star's extreme and irregular dimming. The real intrigue lies in the data gaps. Observations from the Kepler Space Telescope revealed the star's odd behavior, but follow-up studies have been frustratingly inconclusive. Radio telescopes have scanned for artificial signal silence so far. Infrared surveys searched for the heat signature of a Dyson sphere, but the results are ambiguous. The longer the mystery persists, the more it fuels the imagination. If it's not aliens, what natural phenomenon could possibly create such bizarre light patterns? And if it is aliens, why haven't we detected any other signs of their presence? Tabby's star is more than just a cosmic oddity. It's a test case for how we search for extraterrestrial intelligence. It forces us to ask, what should alien technology look like from 1400 light-years away? Would we even recognize it if we saw it? For now, the star keeps its secrets, flickering in the void like a cosmic Morse code we can't decipher. Every new observation brings us closer to an answer, but until then, it remains one of the universe's most tantalizing maybes. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, they carried humanity's hopes into the unknown, but they also carried a mystery. These intrepid probes, hurtling toward the outer solar system, began slowing down in ways no equation could predict. It wasn't much, just a tiny, unaccounted-for deceleration, about 10 billion times weaker than Earth's gravity. But in the precision-driven world of astrophysics, even a whisper of unexpected motion screams for explanation. Dubbed the Pioneer Anomaly, this subtle but persistent deviation became one of space exploration's most stubborn puzzles. At first, scientists assumed it was a simple engineering issue, perhaps heat radiating unevenly from the probe's nuclear power sources, nudging them off course like a gentle breeze on a sail. But when they crunched the numbers, thermal radiation could only explain part of the drift. The rest defied logic. Could unseen clouds of dark matter be tugging at the spacecraft? Or was there a fundamental flaw in our understanding of gravity itself? Some theorists even floated the idea of modified inertia, a tweak to Newton's laws that would account for the anomaly at extreme distances from the Sun. The plot thickened when newer spacecraft, like the New Horizons probe, didn't exhibit the same behavior. This inconsistency turned the Pioneer Anomaly into a cosmic detective story. If the effect was real, why didn't it affect all deep space missions equally? Then, just as mysteriously as it appeared, the anomaly faded. By the 2000s, as the aging Pioneers lost power and contact, their unexplained deceleration seemed to lessen, or perhaps our measurements simply couldn't detect it anymore. The vanishing act left physicists with more questions than answers. What makes this enigma so compelling isn't just the scientific challenge. It's the humbling reminder that even our most trusted models of the universe might be incomplete. The pioneers, those silent ambassadors of human curiosity, may have stumbled upon a crack in the foundation of physics. Whether the culprit was mundane or revolutionary, the anomaly underscores a thrilling truth. Sometimes the universe's quietest whispers hold the loudest lessons. The moon has always been our silent companion, a barren world pockmarked with craters. So why do ancient lunar rocks tell a story of ferocious magnetic storms? Today, the moon's magnetic field is practically non-existent, a ghost of what it once was. But billions of years ago, it crackled with magnetic energy strong enough to rival Earth's. Here's the puzzle. Magnetic fields require churning molten metal cores like Earth's iron dynamo. Yet the moon is far too small to have kept its core molten for long. So how did it pull off this cosmic sleight of hand? The answer might rewrite not just lunar history, but our understanding of how rocky worlds evolve. When Apollo astronauts brought back moon rocks in the 1960s and 70s, scientists were stunned. Tiny mineral grains in those samples were magnetized, frozen in time like compass needles pointing to an ancient field. The strength of this field was staggering at its peak. Around 3.5 billion years ago, the moon's magnetism might have been even stronger than Earth's is today. That's like a campfire outshining a bonfire. The numbers just didn't add up. A body as small as the moon should have cooled rapidly after formation, its core solidifying within a few 100 million years. Without a swirling, molten core, there's no engine to power a magnetic shield. So what kept the moon's dynamo running for over 1 billion years? One theory points to cosmic violence. The moon's early days were chaotic, bombarded by asteroids the size of mountains. A colossal impact could have kicked the lunar core back into motion, like stirring a dying ember to reignite the flame. Simulations show that such a collision might have disrupted the moon's interior, creating turbulent currents that temporarily revived its magnetic field. But there's a catch. The field persisted far longer than these models can explain. Another idea suggests the moon's orbit played a role. Early in its history, the moon was much closer to Earth, and our planet's gravitational pull might have stretched and squeezed its interior, generating heat through friction, a process called tidal heating. Think of it like repeatedly bending a paperclip until it gets hot. This could have kept the core simmering, but critics argue the effect wouldn't have been strong enough to sustain such a powerful field. Then there's the wild card, precipitation-driven dynamos. Recent experiments suggest that as the moon's molten core cooled, solid iron crystals might have sunk toward the center, while lighter elements rose. This movement, like blobs of wax in a lava lamp, could have generated electrical currents and a magnetic field. It's an elegant solution, but it still doesn't fully account for the field's surprising intensity. What makes this mystery so thrilling is what it implies about other worlds. If small, seemingly inert bodies like the moon once harbored magnetic shields, could the same have been true for Mercury, Mars, or even distant exoplanets? Magnetic fields act as invisible armor, deflecting deadly solar radiation and preserving atmospheres. Without one, Mars lost its water and air, becoming the desert we see today. The moon's ancient dynamo hints that magnetic fields might flicker on and off in ways we're only beginning to grasp, raising the tantalizing possibility that even dead worlds might have had moments of hidden vitality. For now, the moon guards its secrets closely. Future missions like NASA planned Lunar Rover Viper or Artemis-era sample returns might uncover fresh clues buried in the regolith. Until then, this magnetic enigma stands as a reminder that even our nearest celestial neighbor still has the power to surprise us. After all, if something as quiet as the moon was once a swirling, magnetic maelstrom, what other cosmic surprises are waiting just next door? Hidden behind the Milky Way's thick veil of dust and stars, something colossal is pulling thousands of galaxies toward it. An invisible force so powerful it bends the very fabric of our local universe. This is the Great Attractor, a gravitational anomaly that defies explanation. Picture standing in a river, feeling the current tug at your legs, but instead of water, its entire galaxies drifting toward some unseen waterfall in the cosmos. The effect is unmistakable. From our vantage point, everything in our galactic neighborhood, the Milky Way included, is moving toward this mysterious point in space at over 2 million kilometers per hour. But when astronomers try to look directly at it, they hit a wall. Literally, our own galaxy's dense disk of dust and gas blocks the view, leaving us blind to whatever lurks in that direction. What could possibly exert such a pull? The first clue came in the 1970s, when scientists noticed galaxies weren't just spreading apart from the Big Bang. They were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. At first, they assumed it was just a massive cluster of galaxies, maybe a supercluster like the nearby Laniakea, which includes our own Milky Way. But when they estimated the mass needed to account for the motion, the numbers were staggering. Even the largest known superclusters couldn't explain the gravitational grip of the Great Attractor. It's like tossing a handful of marbles onto a trampoline and watching them all roll toward a hidden bowling ball you can't see. Then came the plot twist. As telescopes peered deeper, they found something even stranger behind the Great Attractor. The Shapley supercluster, a monstrous gathering of galaxies over 4 times more massive than expected. Could this be the true source of the pull? Some researchers think the Great Attractor might just be a waypoint, a stepping stone in our galactic journey toward Shapley's immense gravity. Others argue there's still missing mass, perhaps vast clouds of dark matter or structures we haven't even detected yet. But here's the real mind bender. The Great Attractor isn't just pulling us. It's part of an even larger flow, a cosmic conveyor belt that includes distant galaxy clusters all moving toward the same incomprehensible destination. This suggests something far grander than a single supercluster, a web of gravity woven across scales we're only beginning to map. It's as if the universe has hidden its largest structures behind a cosmic curtain, revealing just enough to keep us guessing. Unraveling this mystery could rewrite our place in the cosmos. If the Great Attractor is a flaw in our understanding of gravity, it might hint at new physics. If it's a sign of something even bigger, it could force us to redraw the boundaries of our cosmic neighborhood. For now, it remains a shadowy titan, its secrets locked behind the Milky Way's dusty blindfold, a reminder that sometimes the universe's most profound truths are hidden in plain sight, waiting for us to look in the right direction. Deep in the constellation Serpens, a dead star spins at dizzying speeds, and circling it is something even more astonishing. Meet Quasar J1719-1438b. A planet that shouldn't exist, forged from the very stuff of dreams. Imagine a world not of rock or gas, but of solid crystallized carbon, a diamond the size of Jupiter, glittering in the eternal night of space. This isn't science fiction. It's a real celestial oddity that defies everything we know about how planets form. The story begins with its host, a pulsar, the corpse of a massive star that went supernova, leaving behind a rapidly spinning neutron star no larger than a city. Pulsars are among the most hostile environments in the universe, bombarding their surroundings with lethal radiation and gravitational forces powerful enough to shred ordinary planets. Yet somehow this diamond world survived. Astronomers discovered it in 2011 when they noticed the pulsar's radio pulses wobbling slightly, betraying the presence of an orbiting companion. What they found was staggering, a planet denser than any known, composed almost entirely of carbon compressed into crystalline perfection. How does a diamond planet even form? The leading theory is as dramatic as it is unlikely. Once, this world might have been a massive star itself, locked in a cosmic dance with its partner. When the partner went supernova, the blast stripped away the outer layers of the diamond planet's predecessor, leaving behind a core so rich in carbon that the intense pressure transformed it into a celestial jewel. Think of it like a cosmic smelter taking a star's heart and crushing it into the hardest substance known to science. But here's what really boggles the mind. This planet orbits its pulsar in just 2 hours. That's closer than Mercury is to our Sun, meaning its surface is bathed in deadly radiation and tidal forces that should have torn it apart eons ago. Yet there it sits, a defiant cosmic diamond refusing to shatter. Its very existence forces us to rewrite the rules of planetary survival. If worlds can form and persist in such extreme conditions, what other impossible planets might be lurking in the pulsar's shadow? The discovery also raises a tantalizing question. Are diamond planets rare flukes, or could they be more common than we thought? Carbon-rich stars are scattered across the galaxy, and if even a fraction of their remnants crystallized, the universe might be littered with these glittering anomalies. Some scientists speculate that beneath the clouds of gas giants like Jupiter, there could be layers of diamond rain whole oceans of gemstones waiting to be discovered. PSR J1719-1438b isn't just a scientific curiosity. It's a beacon of the universe's boundless creativity, a world born from stellar catastrophe, forged in unimaginable pressures and polished by time into something almost mythic. It reminds us that out there in the dark, the cosmos is still writing stories stranger than anything we could invent, and sometimes those stories shine. Galaxies should be cosmic whirlpools, graceful spirals where stars orbit in predictable harmony, held together by gravity's unbreakable grip. But out in the deep reaches of space, some galaxies laugh in the face of this expectation. They spin so wildly fast that, by all known laws of physics, they should fling their stars into the void like a runaway carousel. Yet somehow, against all odds, these galactic daredevils hold themselves together. It's as if the universe handed them a different rulebook, one where gravity's limits don't apply. Take NGC 1052, a spiral galaxy over 60 million light-years away. Its outer stars race at speeds that should send them careening into intergalactic space, yet they cling stubbornly to their orbits. The numbers don't add up. Based on the visible matter we can detect, there's simply not enough gravity to keep these stars from escaping. So what's holding them in place? The leading suspect is dark matter, the invisible glue thought to make up most of the universe's mass. If these galaxies are embedded in vast halos of dark matter, their extra gravitational pull could explain the impossible speeds. But here's the catch. Some of these rebel galaxies show too much dark matter, far more than our models predict. It's like stepping on a scale and finding you weigh twice what your body suggests possible. Then there's the even more radical possibility. What if dark matter isn't the answer at all? A handful of physicists argue that we might need to rewrite the laws of gravity itself. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at galactic scales, strengthening just enough to keep fast-spinning galaxies intact without invoking unseen matter. It's a controversial idea, but the stubborn persistence of these galactic speed demons keeps the debate alive. After all, if our understanding of gravity works perfectly in the solar system but fails catastrophically in galaxies, maybe the problem isn't the missing matter. Maybe it's the math. The most fascinating part, these impossible galaxies aren't rare exceptions. They're everywhere, from the ultra-diffuse Dragonfly 44, which spins like a cosmic frisbee despite being nearly invisible, to the bizarre super spirals that rotate twice as fast as the Milky Way. The universe seems obsessed with flouting its own rules. Each one is a cosmic rebellion, a silent protest against our tidy models of how galaxies should behave. What makes these galactic anomalies so thrilling isn't just the mystery, it's what they reveal about the universe's personality. The cosmos isn't some rigid, predictable machine. It's a place of chaos and creativity where the rules are more like suggestions. Whether the answer lies in dark matter, new physics, or something we haven't even imagined yet, these spinning enigmas remind us that the universe still has secrets tucked in its pockets, and it's not done surprising us. We think we know what the universe is made of: stars, planets, gas, and dust. But here's the cosmic twist: half of the ordinary matter, the stuff that makes up everything we can see and touch, is missing. Gone, vanished without a trace. Scientists call this the missing Baryon problem, and it's one of the most perplexing gaps in our understanding of the cosmos. Baryons, the particles that include protons and neutrons, should be everywhere, woven into the fabric of the universe in a vast, invisible network known as the cosmic web. Supercomputer simulations show this web with stunning clarity. Tendrils of gas stretching between galaxies like threads in a spider's silk. But when astronomers look up at the sky, they only find about half the baryons the models predict. So where is the rest of the universe's ordinary matter hiding? The first clue came when researchers realized that the missing baryons weren't truly missing. They were just incredibly hard to see. Ordinary matter doesn't just clump into stars and planets. Most of it exists as diffuse, superheated gas floating in the spaces between galaxies. This gas isn't cold and dense enough to glow like a star, nor is it hot enough to emit bright X-rays. Instead, it lurks in a lukewarm state, invisible to most telescopes. To find it, astronomers had to get creative. They turned to distant quasars' brilliant beacons powered by supermassive black holes, and studied how their light filtered through the cosmic web. Like shining a flashlight through fog, the quasars revealed faint absorption lines in their spectra, betraying the presence of ionized oxygen and other elements in the intergalactic medium. These observations confirmed that some of the missing baryons were there all along, hiding in plain sight as a ghostly million-degree haze. But even with these detections, the numbers still don't quite add up. The missing baryons aren't just floating loosely, they are also tied up in structures we're only beginning to map. Some might be locked inside enormous reservoirs of warm, hot intergalactic medium, or WIM, a theorized but elusive component of the cosmic web. Others could be hiding in galaxy clusters, where gravity compresses gas into filaments too faint to detect. Then there's the wild card. Could some of these baryons exist in forms we haven't yet imagined? Some theories suggest they might be tied up in exotic particles or even leaking into extra dimensions, though these ideas remain speculative. What makes this mystery so compelling isn't just the hunt for hidden matter. It's what the solution could reveal about the universe's architecture. The cosmic web isn't just a backdrop, it's the scaffolding upon which galaxies are built. Understanding where the missing baryons are could help us piece together how galaxies form, how they evolve, and even how the universe itself is structured on the largest scales. It's like trying to understand a city by studying its streets, only to realize half the roads are invisible. The search for these missing baryons is far from over. New telescopes, like the upcoming Athena X-ray Observatory, promise to peer deeper into the WIM and other elusive structures. Meanwhile, advances in simulations are helping scientists refine their predictions, narrowing down where to look next. Every discovery brings us closer to completing the cosmic inventory, but for now, the universe's missing matter remains one of its most tantalizing puzzles. After all, if we can't even account for half the ordinary stuff in the cosmos, what else might we be overlooking? In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: a visitor from interstellar space, tumbling past the sun at breakneck speed. They named it Oumuamua, Hawaiian for scout or messenger from afar. At first glance, it seemed like just another space rock, albeit one from beyond our cosmic neighborhood. But the closer scientists looked, the more bizarre Oumuamua became. Its shape alone was enough to raise eyebrows, long and thin like a cosmic cigar, spinning end over end in a way no natural object ever observed had done before. Then came the real shocker. As it hurtled away from the sun, Oumuamua sped up, an acceleration that couldn't be explained by gravity alone. Comets sometimes get a boost from vaporizing ice, but Oumuamua showed no signs of a tail or outgassing. It was as if some unseen force was pushing it forward. Theories exploded faster than a supernova. Some scientists speculated it might be a cosmic iceberg, a chunk of pure hydrogen ice, invisible to telescopes, slowly evaporating in sunlight and giving it that mysterious kick. Others suggested it could be a fragment of a shattered planet, torn apart by its star's gravity and sent careening across the galaxy. But the most electrifying idea came from Harvard astrophysicist Avi Loeb, who proposed Oumuamua might be artificial, a solar sail or derelict probe from an advanced civilization, harnessing sunlight for propulsion. After all, humanity has already launched light sail prototypes. Who's to say another species hadn't perfected the technology? Skeptics pushed back hard. If Oumuamua was an alien artifact, where were the radio signals? Why no visible signs of technology? The lack of definitive evidence left the door open for more mundane explanations. Perhaps it was a rare type of ultra-porous asteroid, its lightweight structure reacting unpredictably to solar radiation. Or maybe it was a tidal disruption fragment, a piece of a planet shredded by a black hole, stretched into that peculiar shape before being ejected into the void. The debate rages on because Oumuamua is gone forever, vanishing into the depths of space before we could get a clear look. No other interstellar visitor since, not even the more recent Borisov, has behaved so strangely. That fleeting glimpse has left astronomers with more questions than answers. Was it a natural oddity, a fragment of some cosmic catastrophe we've never witnessed? Or was it, as some still dare to wonder, our first brush with something designed by minds beyond our own? What makes Oumuamua so tantalizing isn't just its mystery, it's the unsettling possibility that we might never solve it. In the vast darkness between stars, countless more objects like it could be drifting unseen, each carrying secrets of how the universe builds, or perhaps even inhabits, its wandering stones. Until the next interstellar scout arrives, Oumuamua remains a cosmic Rorschach test, reflecting back whatever we're most eager to see, the familiar or the extraordinary. One thing's certain, the universe is far stranger than we've dared to imagine. The universe is supposed to be fair, no favorite directions, no cosmic north or south. Everywhere you look, the same rules should apply. But in 2005, cosmologists stumbled upon something that shattered this assumption. Buried in the oldest light we can see, the cosmic microwave background, or CMB, was a pattern so peculiar they called it the axis of evil. This wasn't just some random nickname. It was a direct challenge to one of the most sacred principles in cosmology, isotropy, the idea that the universe looks the same in all directions. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. In theory, its temperature fluctuations should be random, like static on an old TV. But when scientists mapped this ancient light, they found strange alignments, large-scale temperature patterns that seemed to point in a specific direction, as if the universe had secretly picked a preferred axis. It's like rolling 1,000 dice and finding they all land on 6 over and over. The odds of this happening by chance are astronomically low, yet there it was, etched into the fabric of reality. Some dismissed it as a fluke, a trick of statistics, or an artifact of incomplete data. But as measurements improved, the anomaly refused to vanish. If anything, it grew more pronounced. The so-called axis of evil wasn't just a blip. It was a cosmic fingerprint, something fundamental we'd overlooked. The implications were staggering. If the universe isn't isotropic, then our entire understanding of its birth and evolution might need a rewrite. The Big Bang predicts uniformity, not patterns that whisper of hidden structures. One radical explanation points to the multiverse. If our universe is just one bubble in an infinite foam of others, perhaps the axis of evil is a bruise, a mark left by a collision with a neighboring universe in the distant past. It's a wild idea, but not impossible. Other theories suggest primordial magnetic fields or gravitational waves from the universe's first moments might have imprinted this odd alignment. Then there's the unsettling possibility that we're seeing the shadow of something even stranger, a flaw in spacetime itself, a cosmic tilt that warps our perception of reality. The axis of evil isn't just a scientific curiosity, it's a philosophical lightning rod. It forces us to ask, is the universe truly random, or are we missing a deeper layer of order? For now, the anomaly lingers, a silent challenge to our models and our egos. Whether it's a clue to the multiverse or just a cosmic coincidence, one thing's certain: the universe has a way of humbling us, reminding us that even its oldest light still holds secrets we're only beginning to decipher. In the early universe, just 700 million years after the Big Bang, something impossible blazed to life, a quasar, so bright it outshone entire galaxies, powered by a black hole with the mass of 12 billion suns. Known as SDSS J0100+2802, this cosmic monster defies every rule we have about how black holes grow. Think of it like finding a skyscraper in the middle of the Stone Age, a structure so advanced it shouldn't exist for billions more years. Yet there it was, lighting up the infant cosmos like a flare in the dark. The problem isn't just its size, it's the timeline. Black holes form from collapsing stars, slowly growing by swallowing gas and merging with others. For SDSS J0100+2802 to reach its staggering mass so quickly, it would have needed to feast non-stop, gobbling up matter at the theoretical maximum rate for its entire existence. Even then, the math barely works. It's like trying to explain how a toddler bench pressed a truck. The physics just doesn't add up. Some scientists argue that the first black holes might have formed differently, perhaps from the direct collapse of massive gas clouds in the universe's chaotic early days, skipping the star stage entirely. These direct collapse black holes could have been born giants, giving them a head start. But even this theory strains to account for the quasar's ridiculous brightness and size. Then there's the nuclear option. What if our cosmic clock is wrong? The age of the universe is pinned down by multiple lines of evidence, from the cosmic microwave background to the expansion rate of space. But could there be a flaw in how we measure these early epochs? If the universe is even slightly older than we think, it might buy enough time for such a quasar to form. Alternatively, maybe black holes in the early universe had access to some exotic fuel, dark matter annihilation, or primordial quantum effects that let them grow at breakneck speeds. What makes this quasar so thrilling isn't just the mystery, it's the way it forces us to rethink the cosmic rulebook. Every time we push our telescopes deeper into the past, we find these outrageous outliers, objects that shouldn't exist yet do. They're like cosmic boundary pushers, testing the limits of what's possible. If black holes can grow this fast, what does that mean for galaxy formation? Could there be even larger monsters lurking in the early universe, waiting to be discovered? For now, SDSS-J0100 plus 2802 stands as a defiant challenge to our models, a beacon from the past that refuses to fit neatly into any box. Whether it's evidence of new physics, a flaw in our timelines, or something even stranger, one thing's clear: the early universe was far more dynamic and far more mysterious than we ever imagined. Imagine a universe where everything you can see, every star, planet, and swirling galaxy is just the tip of the iceberg. The rest, an invisible ocean, vast and mysterious, shaping the cosmos in ways we can measure but not see. This is the enigma of dark matter, the universe's most persistent ghost. It doesn't emit light, reflect it, or absorb it, yet its gravitational grip is so powerful that without it, galaxies would fly apart like spinning tops, losing their balance. The numbers are staggering. For every ounce of visible matter, the stuff that makes up you, me, and every glowing star, there's 5 times more dark matter silently holding the cosmic fabric together. The story of dark matter begins with a cosmic detective story. In the 1930s, astronomer Fritz Zwicky noticed something odd about the Coma cluster, a group of galaxies over 300 million light-years away. The galaxies were moving so fast that the cluster's visible mass couldn't possibly hold them together. It was like watching a merry-go-round spin so violently that its steel frame should shatter, yet somehow it stayed intact. Zwicky proposed the existence of dunkle materie, or dark matter, to explain this gravitational glue. But it wasn't until the 1970s that Vera Rubin's groundbreaking work on galaxy rotation curves confirmed the anomaly. Stars at the edges of spiral galaxies orbit just as fast as those near the center, defying Newton's laws unless some unseen mass is propping up the system. So what is dark matter? The leading theory points to WIMP, weakly interacting massive particles, hypothetical subatomic particles that barely interact with normal matter except through gravity. Think of them as cosmic neutrinos on steroids, passing through you right now by the billions without a trace. But despite decades of hunting with ultra-sensitive detectors buried deep underground, not a single WIMP has been caught. That's led to other intriguing possibilities. Could dark matter be made of actions, ultra-light particles theorized to solve a different quantum puzzle? Or primordial black holes, remnants of the Big Bang lurking unseen? Some physicists even speculate about mirror matter, a parallel universe of particles identical to ours but invisible, sharing space with us like ghosts in the machine. Then there's the radical alternative. Maybe dark matter doesn't exist at all. A vocal minority of scientists argue that what we're seeing isn't missing matter but a flaw in our understanding of gravity. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently at galactic scales, eliminating the need for dark matter entirely. It's a compelling idea, except for one problem. When astronomers study colliding galaxy clusters like the famous Bullet cluster, they find that the gravitational lensing effects which bend light like a funhouse mirror don't align with the visible matter. Instead, they match the expected distribution of, you guessed it, dark matter. It's as if the universe is trolling us, dangling clues that refuse to fit neatly into any theory. The most tantalizing part, dark matter might not be just one thing. It could be a mixture of particles or even something beyond particles, a cosmic fluid, extra-dimensional effects, or quantum fields we haven't discovered yet. Every time we think we're closing in, the mystery deepens. Experiments like the Large Hadron Collider hunt for dark matter particles in high-energy collisions. Space telescopes map its distribution by tracing how it warps the light of distant galaxies. Yet after all this effort, dark matter remains the universe's ultimate tease, everywhere and nowhere at once. What keeps scientists awake at night isn't just the puzzle itself, it's what solving it could reveal. Dark matter isn't just glue holding galaxies together. It's the scaffolding upon which the entire universe is built. The first stars, the earliest galaxies, the very structure of reality as we know it, all owe their existence to this invisible architect. If we ever crack its code, we won't just find a new particle, we'll unlock a hidden chapter in the story of existence. Until then, dark matter remains the universe's greatest unread book, its pages written in gravity, waiting for us to learn the language. The Big Bang was supposed to be the ultimate cosmic alchemist, transforming raw energy into the building blocks of everything we see. Hydrogen, helium, and a pinch of lithium were forged in those first fiery minutes, leaving an elemental fingerprint we can still measure today. But when scientists tally up the lithium in the universe, something doesn't add up. There's only about 1/3 of the lithium we should see. It's like baking a cake with all the right ingredients, only to find half the sugar mysteriously vanished before the first bite. This cosmic accounting error is known as the missing lithium problem, and it's been haunting astronomers for decades. The mystery starts with nucleosynthesis, the process that created light elements in the universe's infancy. Based on the temperature and density of the early cosmos, precise calculations predict how much lithium-7, a specific isotope, should have formed. Those numbers match beautifully for hydrogen and helium, but lithium falls woefully short. At first, researchers thought stars might be the culprits, burning up the extra lithium over billions of years. But here's the twist. When they measured lithium in the oldest stars, celestial relics nearly as ancient as the universe itself, the levels were even lower than expected. If anything, these primordial stars should have preserved the Big Bang's original lithium, not destroyed it. It's as if the universe lost its lithium before stars even had a chance to meddle. So where did it go? One possibility is that lithium is hiding in plain sight, trapped in regions we can't easily observe. Between stars, vast clouds of gas might contain reservoirs of lithium that blend into the background, invisible to our telescopes. Another theory suggests that lithium could be settling into the cores of stars, sinking out of sight due to its relatively heavy atomic weight. But even these explanations struggle to account for the staggering deficit. Then there's the more radical idea. What if our understanding of the early universe is incomplete? Could unknown particles or forces have altered lithium production in those first chaotic moments? Some theorists propose that exotic dark matter interactions might have disrupted nucleosynthesis, leaving us with less lithium than the models predict. The stakes are higher than they seem. Lithium isn't just a trivial ingredient, it's a critical clue to the universe's earliest chapters. If our predictions are wrong, it might mean we're missing a fundamental piece of how matter behaved under extreme conditions. This puzzle even connects to the cosmos on the largest scales, since the same physics governing lithium production also influences how galaxies form and evolve. Every time we measure lithium in a distant star or a gas cloud, we're essentially fact-checking the Big Bang's recipe book. The search for answers continues with cutting-edge tools. Astronomers now use high-resolution spectrographs to hunt for lithium in stars and interstellar gas, while particle physicists simulate the conditions of the early universe in labs. Each new observation tightens the constraints, narrowing down the possible explanations. But for now, the missing lithium remains a quiet reminder that even our most cherished cosmic models might still have pages left to fill. After all, if we can't account for something as simple as an element's abundance, what other surprises might the universe be hiding? History books tell us the year is 2024, but what if they're wrong, not by a few years but by centuries? Enter the phantom time hypothesis. one of the most audacious claims in historical revisionism, that 300 years of the past never actually happened. According to this fringe theory, the period between the 6th and 9th centuries was fabricated a grand conspiracy orchestrated by medieval rulers and the Church to rewrite chronology. If true, it would mean Charlemagne never existed, the Dark Ages were a fiction, and our entire cosmic timeline is off by generations. It sounds like the plot of a Dan Brown novel, but this idea has stubbornly lingered in the shadows of academia, challenging not just history, but our understanding of celestial events tied to those phantom centuries. The theory traces back to German historian Herbert Illig in the 1990s. He noticed odd gaps in the archaeological record and inconsistencies in dating methods like dendrochronology, the study of tree rings. The Gregorian calendar, introduced in 1582, supposedly corrected a 10-day drift caused by an overcount in leap years. But Illig argued the math was off. The real discrepancy should have been 13 days, suggesting those extra 3 days hinted at missing centuries. He pointed to eerie silences in architectural and literary evidence from the supposed Carolingian Renaissance, as if an entire era had been airbrushed from reality. To believers, it's as if someone hit delete on 300 years and no one noticed. But here's where astronomy throws a wrench into the theory. Events like solar eclipses and planetary alignments are cosmic clocks, meticulously predictable backward and forward in time. Records from China and the Middle East describe eclipses during the phantom period that match our modern calculations precisely. If those 300 years were invented, how could ancient observers have predicted celestial events that, according to the hypothesis, hadn't occurred yet? Skeptics also highlight radiocarbon dating, which independently verifies the age of artifacts from the disputed era. A global conspiracy to forge tree rings, ice cores, and star charts stretches credulity beyond breaking point. Yet the phantom time hypothesis taps into a deeper unease: how fragile our grip on history really is. Before modern record-keeping, timelines were pieced together from fragmentary chronicles, often rewritten for political or religious reasons. Small errors compound over centuries, misplaced decimal points in carbon dating, misinterpreted texts, or even deliberate falsifications. While the 300-year gap is almost certainly fantasy, it raises valid questions about how we reconstruct the past. For astronomers, this isn't just academic. Cosmic events anchor human history: supernovas recorded by ancient scribes, comets that heralded revolutions, and if our chronology is even slightly skewed, it could distort our understanding of stellar life cycles or galactic evolution. What makes this idea so magnetic isn't its plausibility, but its audacity. It forces us to confront how much of history rests on trust in systems and scribes long turned to dust. Most scientists dismiss it as pseudo-history, yet its persistence speaks to a timeless truth. The past is a story we tell ourselves, and sometimes the most compelling stories are the ones that make us question the very pages they're written on. Whether as a cautionary tale or a fringe curiosity, the phantom time hypothesis reminds us that history, like the universe, is full of shadows, and not all of them are empty. Picture this: floating in the infinite void of space, a fully formed brain suddenly pops into existence, complete with memories, thoughts, and the vivid illusion of an entire life. No body, no world, just a lone consciousness hallucinating reality into being. This isn't the plot of a sci-fi horror story. It's the Boltzmann brain paradox, one of the most unsettling thought experiments in modern physics. Named after 19th century physicist Ludwig Boltzmann, the idea emerges from a chilling implication of entropy and infinity. Given enough time, random quantum fluctuations could theoretically assemble particles into any configuration. no matter how improbable, including a self-aware mind that believes it's a real person living in a real universe. At its core, the paradox grapples with the nature of probability in an eternal cosmos. In a universe that lasts forever, even the most absurdly unlikely events must happen eventually. Flip a coin enough times and it'll land on its edge. Wait long enough and atoms bouncing around in the void might spontaneously arrange themselves into a functional brain. The math isn't the problem, it's the implications. If Boltzmann brains are possible, then statistically, there should be vastly more of them than real brains like ours, which evolved over billions of years in a stable universe. So how do we know we're not just fleeting aberrations, momentary glitches in the cosmic noise, convinced of our own reality? Critics argue that the paradox is less a scientific dilemma and more a philosophical funhouse mirror. After all, if our memories and observations can't be trusted, if the stars above and the ground beneath our feet might be figments of a disembodied brain's imagination, then the entire foundation of science crumbles. Why trust any experiment or observation if reality itself might be a hallucination? Some physicists dismiss the idea precisely because it's untestable and functionally useless. But others see value in the discomfort it provokes. The paradox forces us to confront the limits of our theories, especially when applied to the far future of an ever-expanding universe where entropy reigns supreme. One escape route lies in cosmology's current leading model: dark energy accelerating the universe's expansion. If space stretches fast enough, it might prevent the infinite time required for Boltzmann brains to form, effectively slamming the door on the paradox. Another solution leans on quantum mechanics, suggesting that conscious observation might play a role in collapsing probability waves, anchoring reality in a way randomness can't mimic. But these are speculations, not proofs. What makes the Boltzmann brain so haunting isn't just the what if, it's what the paradox reveals about our place in the cosmos. It's a reminder that even our most sophisticated models of reality have edges, places where logic frays into surrealism. Whether a quirky intellectual exercise or a genuine cosmic riddle, the paradox underscores a humbling truth: the universe doesn't owe us intuitive answers. In the end, the Boltzmann brain isn't just a challenge to physics. It's a mirror reflecting our deepest anxieties about existence, meaning, and whether anything, even our own minds, can ever be truly certain. From voids that defy cosmic logic to black holes that erase information, these 20 phenomena aren't just curiosities, they're cosmic breadcrumbs, leading us toward truths we haven't even imagined yet. Each one whispers the same humbling message: the universe doesn't play by the rules we've written. It's as if we've been handed a puzzle where half the pieces are missing, and the ones we have keep changing shape. But that's what makes exploration so thrilling. Every anomaly, every paradox is an invitation to dig deeper, to question harder, and to admit that maybe, just maybe, we've only scratched the surface of reality. Think about the implications. The Boötes Void shouldn't exist, yet it does. Dark flow tugs galaxies toward something beyond our sight. Oumuamua accelerated without explanation. These aren't just isolated oddities, they're clues that our textbooks are incomplete. What if the next breakthrough doesn't just fill in a gap but rewrites entire chapters? The history of science is littered with moments like this when the impossible became the foundation of a new paradigm: quantum mechanics, relativity. Dark energy each began as a baffling inconsistency before revolutionizing our understanding. That's the real magic here. These mysteries aren't dead ends, they're doorways. The Fermi Paradox forces us to confront our place in the cosmos. The missing lithium problem hints at flaws in our origin story. Even the Boltzmann brain, as unsettling as it is, challenges us to define what real even means. Science isn't about having all the answers, it's about asking better questions, and right now, the universe is asking some of the best ones yet. So what's next? Maybe you're drawn to the eerie silence of the wow signal, or the way Tabby's star flickers like a faulty streetlight. Perhaps the Great Attractor's gravitational pull keeps you up at night. Whatever captivates you, remember, these puzzles aren't just for astronomers in lab coats. They're for anyone who's ever looked up and wondered. The universe is the ultimate collaborative project, and every curious mind has a role to play. The cosmos is far stranger, far more inventive than we've dared to dream. And that's the most exciting part, because every mystery solved reveals 10 more waiting in the shadows. So keep questioning, keep exploring, and most importantly, stay amazed. After all, the next great discovery might be hiding in the data we've already collected, or lurking just beyond the edge of our telescopes, waiting for someone bold enough to connect the dots. Ready for the next cosmic revelation, neither are we, and that's what makes the journey unforgettable.